twice with two different resulting outputs. So this one is not a function. The inverse for B would be 1, 3, negative 3, 2, 4, 4, 3, 6, and 7, 2. So now let's check that again. I don't have any inputs that are the same. I've got 1, negative 3, 4, 3, and 7. Outputs, I have 3, 2, 4, 6, and 2. So I do have two outputs that are 2, but that is okay for a function. So that is a function. Okay. So now we're going to use these steps to find inverses of our function. So our first step is we change the f of x back to y. That's all we did. Now you're going to reverse your x and y. So it's going to be x equals y plus 3 squared. Then you're going to solve for y. Okay, so the first thing we need to do to undo that square here is going to square root both sides. So you'll get the square root of x equals y plus 3. Then the last thing I need to do is move that 3 to the other side. I know that to do that I need to subtract it from both sides. So I will get y equals the square root of x minus 3. Okay. We're going to show you in a minute how you double check that you really got that. You really do in fact have two inverse functions. So let's go to example number 3. Find, this is telling me the inverse of g of x, g to the negative 1 of x, the inverse of g of x, if negative 8x equals 16. Or sorry, if g of x equals negative 8x plus 16. So we're going to do the same thing again. You've got y equals negative 8x plus 16. Reverse your x and your y. And then solve for y. Reverse x and y, solve for y. So we're going to move that 16 over. We should get x minus 16 equals negative 8y. Then we have to undo that negative 8. So, sorry, over here I should have written it back in function form. So that would have been f to the negative 1 of x equals square root of x minus 3. On this side, our resulting g to the negative 1 of x would equal negative 1/8 x plus 2, and we are done. Okay. Try to do examples 4 and 5 by yourself. Hit pause on your video, and then come back in a moment to check your answers. Okay, now we're checking our answers. So, excuse me. On example number 4, it already has y there instead of a f of x function. So now you're going to reverse those. I need to move that 5 over, so I would get x minus 5 equals y squared. The way I undo a square is to take the square root. So I get the square root of x minus 5 equals y. So y to the negative 1 equals the square root of x minus 5. Lastly, for example 5, I have h of x equals x plus 7 over 2. So change that out to a y, x plus 7 over 2. Reverse my x and my y. And then solve for y. First thing I'm going to do is get rid of that fraction. So I have 2x equals y plus 7. I need to move that 7 to the other side by subtraction. So my h to the negative 1 of x will equal 2x minus 7. So how do we check to see if they are in fact inverses of one another? If we use, this is our function. If I use the inverse of a function as the input for a function, my resulting answer should just be x. The inverses should cancel one another out. So you're using the inverse of the function as the input of the function. Okay? So in this case, and it says, let's use our examples number 4. So for number 4, our original function was x squared plus 5, and we came up with an inverse function of square root of x minus 5. So I'm going to calculate f of f negative 1 of x. This is going to be my input into this function. So my function is x squared plus 5. Instead of x squared, I'm going to use x minus 5. Square root of x minus 5 squared plus 5. I know that when I have the square and the square root of the same quantity, those two quantities cancel out. So x minus 5 plus 5. Remember the reason for that is that the square root here and the square out here canceled each other out, and all you're left is that quantity under the radical. So our negative 5 and our positive 5 cancel. That gives us x. So f of f negative 1 of x does indeed equal x, and they are, this verifies that they are inverse functions. Okay, the next section we'll be working on, still working on module 1.3, is exponential functions and equations. So in this section, you'll be able to determine if an exponential function represents growth or decay, if it's getting larger or getting smaller, and also be able to solve exponential functions using the same base theory. So for exponential functions, the standard form of an exponential function is y equals ab to the x power, where b is the amount that's being changed, x is your exponent, and a is any coefficient that's out in front. So we need to remember that if something is 100%, that is 1.00. So if something is decreasing, it's going to be less than 100% or less than 1.00. If it is increasing, it's going to be greater than 100% or greater than 1.00. Okay, most common ways that you see growth is an interest rate, right? It's the most common. Decay would be a lot of environmental things, okay? Things that are getting smaller. A population might be decreasing by a certain rate. Okay, those are just a couple of examples. Okay, so here's some examples of exponential functions. Y equals 2 to the x, y equals 1/2 to the x, y equals 3 to the negative x. So I want you to first just sketch out y equals 2 to the x. The easiest way to do that is use things that are easy for you to graph. Okay, you can make a quick little table of values. Have an input of 0, 1, and 2. That's easy enough. So we're going to do 2, remember what you're doing, 2 to the x equals our y. So 2 to the 0 power, anything to the 0 power equals what? 1, of course. 2 to the first power would equal 2, and 2 to the second power equals 4. Now you've got some points that you can graph, so we'll go 0, 1, 1, 2, and 2, 4. So exponential graphs make this kind of curvy slope. And this is important. Your graph is not going to go below the x-axis because there is nothing that you can graph that's going to give you a negative output. So even if we have, this is 2 to the 0 power, 2 to the first, 2 to the second. 2 to the negative first is actually 1/2. 2 to the negative second, because of course we know the exponents, when they have a negative exponent, it means reciprocal, so it means 1/2 squared. So that would be 1/4. So that point is way over here, and really close, and as it goes to the left, it's going to get closer and closer to the x-axis, but it's never actually going to touch it. Okay, so this is a typical exponential function graph. Okay, let's do the same thing here. I find it easier to use fractions when graphing, but you can leave the decimals if you want. 0, 1, 2. So 0.5 to the 0, 0.5 to the first, 0.5 to the second. So that's going to, anything to the 0 power is 1, 0.5 to the first is 0.5, 0.5 to the second is 0.25. Be careful of your decimals in here. That's 0.5 times 0.5. Okay, so our graph is 0, 1, 1, and 0.5, and 2, and 0.25. So this graph is actually bending the other direction. See if you can ask yourself why you think that might be and what these two graphs may represent. So this number is what really becomes important. Okay? If this number is greater than 1, 2 is greater than 1, so this is going to represent a growth function. Okay? In this graph, reading from left to right, we're increasing. By the same term, 0.5 is less than 1. That is a decay function. It's getting smaller as we look left to right. Okay? Next page. So I've given you a small kind of chart here that helps you figure out whether something is growth or decay. Okay? The number, the base, is what's going to tell you whether it's growth or decay. In this column, all three are larger than 1. Okay? This number out here doesn't matter. That kind of tells you how skinny or fat your graph is going to be. But, you know, it's how steep or flat the increase is going to be. But it doesn't tell you whether it's growth or not. That's the number right in front of your exponent. Decay is the same thing. 0.5, 1/3, and 4 to the negative x, which is the same as 1/4 to the x, because of course it's a reciprocal. Those are all smaller than 1, so those are all going to be decay functions. Okay? If it is neither, it's because this number is negative and actually flips your graph over. Okay? Because it's the opposite. So for these three, I want you to go ahead and figure out whether you think they are growth or decay functions. Hit pause on your video, come back and check your answers. Okay, so you're back and checking your work. So our B value is what helps us determine whether it's a growth or decay function. For example A, 5 is greater than 1, so this is a growth function. In B, 3 is greater than 1, so it is a growth function. Makes sense, doesn't it? If we're getting more than 100% back, then it should be a growth function. 1/6 is less than 100%. That should be a decay function. So that is a decay function. Okay? Good. So the next topic we will cover is solving equations using the same base. So the idea of same base really utilizes the concept that it's easier to compare two things that are similar. So one of the most common one of the most common exponents that you know is, let's use base 2, because those are the easiest. So 2 squared equals 4. We all know that. That's easy, right? What's another way I can write 4 if I'm writing it in terms of 2? 2 to the second power, right? Basically, the concept of same base is that if I can get these bases to be the same, if I can get them to be the same, then when I solve the equation, I can just set the exponents equal to each other. So for example, if I change this to an equation, and I had 2 to the x equals 4, well, I already know the answer to that question because I know that 2 squared equals 4, but let's use our change of base. So that would change it to 2 to the x equals 2 to what power gives you 4 is the equivalent of 4, 2 squared. Once I have the same base, you can ignore the bases and set your exponents equal to one another, and that is your solution. This is a big thing with logarithms. It's a big thing with solving exponential equations. As soon as you can get them down to the same base, you can ignore the base, set the exponents equal to each other, and solve. And that's what this equation is telling you. If you can get to the same base, then you set the equation equal to each other. Our example up here, we have 32. So they have 2 to the x plus 6 equals 32. Well, that doesn't help us a whole lot unless we can change that 32 in terms of 2. So now you need to ask yourself, well, I think I can multiply something together a few times to get 32. What might that number be? And that number is 2. We're trying to find if that's a power of 2. So 2 to the second is 4, the third is 8, the fourth is 16, the fifth is 32. So 32 is the equivalent of 2 to the fifth. These are the same amount, same value. Once I know I've got the same base, I also know that x plus 6 and 5 must have the same value. So I can set those equal to each other and solve. So x equals 1. Go back and check yourself. Let's double check our work. Okay. 2. I'm sorry, that should be -1, shouldn't it? You're probably yelling at me over the computer. Okay. 2 to the -1 plus 6 equals 2 to the 5th. Well, what's -1 plus 6? 5 equals 2 to the 5th. Those are equal. It checks out. Same base is a big concept, so if you have questions on it, you need to let me know. Okay, so here's our problem that we just did. We changed that 32 to 2 to the 5th. Then we can set them equal to one another. Now we have these, x plus 6 and 5, that we can set equal to one another and solve. And you do indeed get x equals -1, and we already checked that, so we already know that it's true. Okay, let's do example 1 and 2 together. I'll actually work through all these problems together. Okay? You have problems, again, on the top of each of your note packets of work that you need to do on your own. Okay? So let's see. So I have a base here of 3. First thing you need to ask yourself is, can I change 27 to some base of 3? So 3 to the x minus 5. Well, I know that 3 to the third equals 27. This is where, do I have same base? Do you have the same base? Once that answer is yes, you could ignore the base and pull your exponents down and set them equal to each other. X minus 5 is 3. I need to move that over here by addition, so x equals 8. You can always plug that back in up here to check. 8 minus 5 is 3. 3 to the third has obviously got to be the same as 3 to the third, so we know that that's correct. Okay, example 2. Now we don't really have a base. Can you ask yourself, can you square 4 and get 8? No. Is there a base that they might have in common? Could they both maybe be a power of another number? So with exponents, you usually kind of want to start small. So 4 is actually 2 squared. Then we're going to put that exponent right next to it. And the value of 8 is 2 to the third. And again, using parentheses, we're going to do that. Once you have same base, you're going to pull everything down. So you have 2 times 3x plus 5 equals 3 times 4x minus 3. Then you're simply solving. This is easy. Been doing this forever. Not difficult. Right? So you get 6x plus 10 equals 12x minus 9. Move your equations around until you get what you need them to be. So you should get 19 equals 6x. So x equals 19 over 6. Okay? All right. Down here, it's requiring you to remember how we write that exponent there, that value, okay? So if we know that 3 to the third up here was 27, here we've got 1 over 27. Anytime I have 1 over a number, that should click in your head that that's going to be a negative exponent. Okay? So that is simply going to be 3 to the negative third times 3x plus 1. See if I can change my 9 to a base. Well, I know that 3 squared is 9. So I'm going to use that same base of 3. Now I've got the same base of 3. So now I can pull my exponents down and solve. So I get 4x plus 6 equals negative 9x minus 3. Going to kind of move things around here. So 9x is going to come over there. Subtract the 6 out, come over there. So you get 13x equals negative 9. Divide both sides by 13. So my x would equal negative 9/13. Yes, you can have fractions as your solutions, always. Always, always. Okay. So I've got a base over here of x, or excuse me, of 5 with an exponent of x. So that's kind of fine the way it is. This 25 and 5 are not helping me so much. So let's change those both to a base of 5. So 25 is 5 squared. What is square root of 5? Remember that the way you write square roots as a power is x to the 1/2. This is your power. It's x to the first over your root. We're taking the second root. Okay, so times 5 to the 1/2. These would be multiplied together. When you multiply the same base, what do you do with those exponents? You add them. Now that we have same base, we know that we just add those exponents. So x is going to equal 2 plus 1/2. 2 is the equivalent of 4/2 plus 1/2. So x equals 5/2. Okay, and that is change base. And those are your notes for Module 1.3. 3 notes that were not in the first video. This is video part 2. So today we are introducing logarithms, the definition of a logarithm. We already talked about in class that the logarithm is the inverse of an exponent. So they are the inverse of one another, just as adding and subtracting are the inverse of one another, multiplying and dividing are the inverse of one another. Logarithms help us find the power of a number when that power is not a whole number. So far you've dealt with 2 to the third, 2 to the fourth, right? And we know that 2 to the third is 8, 2 to the fourth is 16. But what if I want to know 2 to the what power equals 12? I don't know what that is. I know it's somewhere in between the third and fourth power, but I don't know exactly what. So logarithms are going to help us answer that question. So when we write logarithms in and we say, for example, 2 to some power equals 7. Okay, that means 2 to the x power equals 7. 2 to the x power. That's what we know from writing exponents out, okay? And you will need to be able to convert between exponential and logarithmic equations with great ease. I'm going to emphasize this. This is a really important concept. You must be able to flip back and forth between exponential form and logarithmic form. So, if we're going to convert the first one, let's take 2 to the third equals 8. Okay, let's make this a little bit closer. So, the standard form for a logarithm is the log, you have the base below the line, the answer above it next to log equals your exponent. So, exponential form is something that we're used to. That means 2 to the third power equals 8. The difference with logarithmic form, and I kind of encourage you to think of it like this, it's kind of a circular pattern. 2, the exponent is now what's isolated by itself. 2 to the third power equals 8. It's just rewriting that function, okay? So 5 to the negative second is 1 over 25. The way we write that as a logarithm is log 5, 1/25 equals negative 2. Again, tell yourself, 5 to the negative second equals 1 over 25. Okay? If you kind of make yourself some blanks, kind of helps to fill in. You always know this is going to be your exponent, this is going to be your answer, this is going to be your base. So if we're using 4 to the 5th equals 1,024, 4 is your base, the answer is 1,024, and your exponent was 5. Okay? 2 to the 5th equals x over 2. We don't even need to know what that answer is yet. It's going to be 2 to the 5th equals x over 2. Okay? So now we're going to have some practice writing in logarithmic form, and then by the same token, flipping them around to exponential form. This you have to be very, very adept at. I can't emphasize that enough. We're going to do practice in class. I'm going to quiz you on this. You must be very good at this. Okay? It's not optional. You have to be good at this. So, for example 1a, I know my base is 3. So to convert that to log form, I'm going to log 3. My exponent is going to be out here by itself, and my answer is y. Okay? I'm going to have you go ahead and do B and C on your own. I think you have enough examples to look at, and hit pause on your video, and then come back and check your answers. Okay, now that you're back, let's check to see. So we have log, our base is 3, our answer is 27, so that goes right next to our base, and our exponent is our variable, it's our unknown x. So log 3, 27 equals x. And that's how you would say that, log 3, 27. Okay? For C, our base this time was x, our answer was 32, and our exponent was 5. So some number to the 5th power equals 32. You should also be able to solve these, which you're going to do down lower in example 3. Okay, now let's convert back from logarithmic form, log form, back to exponential form. So I'll help you with A, and then you'll do B and C independently and come back and check your answers. So it's the base to the exponent gives you your answer. So in this case, it would be 3 to the 9th power equals x. Go ahead and try to rewrite B and C, and then come back and check your answers. Hit pause now, please. Okay, so now you should have written your equations in exponential form, not in logarithmic form. So this should have been 2 to the x equals 8, and C would be 5 to the 2nd power equals y. Okay? So now that we know how to do that fairly well, now we're going to solve logarithmic equations. Sometimes it's easier to do that by rewriting it as an exponent. So now we're going to go down, and to me, it's easier to convert this into an exponential equation in order to solve that. So first of all, write that in exponential form. Give you a minute. What I come up with is 3 to the 4th equals x. 3 to the 4th power equals x. Okay? So I know that means 3 times 3 times 3 times 3 equals x, so I should get 81 equals x. For B, it's x to the 3rd power equals 1,000. Something to the 3rd power equals 1,000. The nice thing about multiples of 10 is it's simply that many zeros. So 10, one way you could solve that if you had to was take the cube root of both sides. The cube root of 1,000 is 10, so our x equals 10. I guess we should write that the same direction to be less confusing. Okay? For C, use the circular pattern again. So 2 to the 5th power equals 4x. 2 to the 5th power is 32. Dividing both sides by 4, so x equals 8. So that's the logarithm page for module 1.3. We will be going over these in class, and you will be using logarithmic form more in 1.4 and 1.5.